this at a very low level. I asked a number of mine, I suggested that some of my Physics 272 students come to this lecture. And I said that you will probably understand 3 to 5 slides. Okay? They're in the beginning and they can leave. So,
Are they here?
they are here.
Okay.
Yes, they are here. They're all going to get an A. They didn't realize that. Okay, so actually, how did I get into superconductivity? I'm going to talk about that very briefly. When I was a kid, I got interested in science because of comic books, because this was the only thing I really knew how to read. And there was this guy, Superman, and he had kryptonite. And I said, what the hell is that stuff? And then I realized, well, I'll never be Superman. But there was another comic character. It was this guy. Yeah, Dick Tracy. Okay. Now, Dick Tracy, you notice he's floating around detecting crime with these magnetic cars. So my question is, how did these things work? Okay. And then he said, if the nation that controls magnetism will control the universe, I said, I got to get into this field. And by the way, this statement is relatively true now. He who controls the materials for magnets is controlling a lot of our lives. And notice the Apple Watch. Okay, so I did my PhD on magnetism. Okay, it was on the optical properties of magnets. And then I went to work with Ted Jabal, as Steve said. And my first day with Ted, he says this. Okay, so I said, I wonder what this word is. That was it. Superconductor. So I had to start working on superconductors. So that's how it happened. By the way, some of you may be old enough to know this. Okay. It used to be plastic.
They used to be plastic.
Okay. So what are superconductors? Okay, I think you all know superconductors have no electrical resistance. They were discovered in 1911 by this character here. Totally accidental. Nobody predicted this. Most great discoveries in physics are accidental, as many of you know. Nobody predicted this. They only knew classical mechanics. But even if they had known quantum mechanics, I doubt they would have predicted this phenomenon. Now, zero resistance is not the only thing that happens. There's something called the Meissner effect, which was discovered quite a bit later. And that's the complete expulsion of flux from a superconducting material when you cool it below the transition temperature. That's not explainable by perfect conductivity. So this is actually a separate phenomenon and was very important and, in the theory, in developing the theory. Now I'm also going to talk about the fact there's a critical magnetic field to superconductors. Put too much magnetic field on, you destroy the superconductivity, critical current. All right, how does it happen? Well, this was a hard problem. Here were all the great people who could not solve this problem. All right? And then some phenomenological theories came along after the Meissner effect. And then finally a microscopic theory came. It's a quantum mechanical many-body theory, not something that's easily explainable. Steve Onlager is going to teach a course this spring. I will recommend that you go to it. We will find out what the BCS theory is really all about. Okay? But a very simplistic way of explaining it is that you have, well, first of all, it's known that electrons pair. They form into Cooper pairs. They are bound together with equal and opposite spin. Okay. And how do they pair? Well, a simple way of thinking about it is one electron goes through the lattice, it deforms the lattice, and then the next electron comes along at a later time, sees that deformation, and is effectively attracted to the first electron that went through. So this is, in a sense, a time-retarded interaction. The electrons are never really near one another. But we're going to find out later on with some new superconductors that this mechanism actually doesn't work. And we have to worry about the Coulomb interaction. Okay, so there's, of course, a formula, which is always nice for experimentalists, that comes out of this BCS theory. And just point out that it is related to an average vibrational frequency of the lattice. That's what this Debye frequency is here. Of course, it's also related to the interaction, the electron-proton interaction in some way. But we'll be talking about this fact a little bit later. Okay, so this is most conventional superconductors, in fact, all conventional superconductors, as far as I know, have an L equals 0 state, an orbital L equals 0 state, okay, and the spins are equal and opposite. Okay. Later on, we're going to talk about some superconductors that might have triplet spins. Okay, and there's an energy gap required to break the pairs up. Okay, so where do we find superconductors? This is basically what my research is about, finding materials that are superconducting. Now, Perpetius was a very famous guy when I was in graduate school. He was the man who always could find superconductors. And he had a set of rules for finding them. And here they are, okay? And we're going to find very soon that every one of these rules is wrong. Even the last one. Except for even the last one, which I really felt was very important my whole career, and it's now been destroyed. We actually have to pay attention to yours. We're going to find out. Okay. So it just shows you even supposedly great scientists make a lot of mistakes. He made at least 6 here. All right. So BCS theory worked, and of course it was generalized. The Mathias rules seemed to work. And then came 1986, when copper oxide superconductors were discovered. And I'll tell you more about these, of course. They had transition temperatures above 80 Kelvin. All the prior superconductors had transitions no more than 25 degrees Kelvin. So this was a real breakthrough. Okay. And it turns out, this is kind of what the TC versus time looked like until recently. So this was a real breakthrough in the sense that these materials could go above liquid nitrogen temperature. And of course, there were all sorts of magazine articles about this, and nothing turned out to be true. We don't have any applications of these things at this stage, okay, 35 years later. But from the physics point of view, they're very interesting, because 35 years later, we still do not understand it. And I'm going to go through some of the reasons why we don't understand it, and why it's a very active area of research. So these materials are basically quasi-two-dimensional materials made of copper and oxygen planes, and there are some other ions outside the planes that usually donate or take away electrons. These materials are called strongly correlated materials, and why is that? Okay, if you just look at it ionically and ask what would be the filling of the levels, you find that you have a copper 2+ in here. Copper 2+ is 3d9, there are 90 electrons instead of 10. So if you now think about band theory, you will have a highest energy D band, which is got 1 electron in it. And most bands, a filled band will have 2 electrons in it. Okay, so a band with 1 electron in it should be a metal. And yet these materials are not metals. They're insulators. But they are not your typical band insulator. They're insulated because of strong Coulomb interactions. So in other words, electrons on one copper do not want to jump to the next electron because to the next copper because of very strong Coulomb interactions between the electrons. So this is called a Mott insulator, a different type of insulator, and it shows that these copper oxides are what we call strongly correlated materials. And the whole problem of the physics of strongly correlated materials is, in essence, not very well understood. So copper oxides are not alone. There are many other materials that I'll show you that also are strongly correlated materials. And this is a very active area of research now to try and understand strongly correlated materials. So this is a picture of the copper oxide plane. And actually there are spins on the coppers, so the coppers have a spin, and there's basically an exchange interaction between the electrons on the coppers, which leads to antiferromagnetism, and you have no electrons or holes built into the system. So that's what these little arrows mean. You have an antiferromagnetic array of copper spins. So now, of course, we want to know how do they become superconductors. So you dope them, and the phase diagram. It looks like this as you dope. The antiferromagnetism is killed and superconductivity appears and a high TC superconductivity. So one of the whole goals of this field is to understand how is this happening. Okay? And I'm not going to go into the details of this, other than to say there have been a lot of theoretical papers written about this topic, probably over 100,000, and there's probably over 100,000 experimental papers being done on this problem. And I'm going to try and sum up in 3 slides what we know and don't know about this stuff. But basically, these materials are now called doped charge transfer insulators. That's just because the electrons or the dopants are actually in the oxygen orbital and not in the d orbital. And the energy gap is this charge transfer energy, not the Coulomb energy, which is called U. But there are various models to this that I'm not going to go into. And to dope it, if you want to put holes into the system, you dope with strontium. If you want to put electrons in, you dope with cerium. I'm going to talk mostly about what happens when you put electrons in. And the schematic way of thinking about this is the 2-dimensional Fermi surface. Those of you who aren't matter physicists don't have to worry about what the Fermi surface means, but basically this shaded region is the region of filled states that occur in this material. Okay. So what's the phase diagram of these cuprates look like? Very complicated. This is now the phase diagram of whole doped cuprates, where you basically take a carrier out of a band. That's a whole doped material. So you're taking basically a carrier out of the oxygen P band, and as a function of doping, you have antiferromagnetism disappearing, but you also have other types of orders that are coming in. You have something called charge order, you have pneumatic order. There's a lot of things going on that actually nobody understands even to this day. And there seems to be this line coming down. It's not a phase transition, but it delineates a region up here that's called the strange metal region, which I will talk more about, and something called the pseudogap. And neither the strange metal nor the pseudogap are understood in detail what's going on. And obviously they've got to be important for the superconductivity, because here's the superconductivity that's occurring all around these things. And when you go to very high doping, you end up back in a normal metallic state. Okay, that was the phase diagram in 2015. This is the phase diagram now, and this is what I'm going to talk a little bit about in this talk. And the only difference really in these phase diagrams is this region, this normal state region called the strange metal, is actually more spread out in doping than it was in the other diagram. Okay, so fine. Now, what's the mechanism of superconductivity? That's why I walked in here, right? To find out. And the answer is
7.
right. 7. It was 41.
That was last week.
Oh, 41. Okay. So, of course, there's many proposals, because theorists are very creative. And this is only a small list of the proposals that have gone on. But phonons pretty much can be ruled out because of the following reason, that each proposal has a different orbital symmetry with a superconducting wave function. So, for example, phonons are pretty much expected to be S-ray or L equals 0 orbital part of the superconducting wave function. But what's been found in the cuprates is that the orb parameter is D wave, L equal 2. I'll show you in a minute what that means. Okay, so it's likely that there's some kind of magnetic interaction that's causing the superconductivity, okay, which means it's a Coulomb interaction of some kind. Somehow the Coulomb interaction, which we think of as being very repulsive, can, in some situations, be actually attractive. And this has been actually known for, I think, since the 60s, even before I was getting my PhD, but I certainly didn't know about it. As far as I was concerned, all superconductors have S-wave symmetry. So it was a big surprise to me when these other symmetries came up. Okay, and I'll show you in a minute, this is what I mean by something that has a different symmetry. something with a so-called S wave, has the superconducting gap function that's isotropic over the Fermi surface. So the density states might look something like this. Remember, there's an energy gap in a superconductor. That's why it forms the Cooper pairs. That energy is what gives you superconductivity. You have to put energy in to break the pairs apart and destroy the superconductivity. A D-wave gap is something that looks like this. The D part of the orbit of the wave function changes sign, and there's a region where actually there is no gap, called the node. So the density space looks like this. This is not important for understanding anything I'm going to say. In fact, there's not much that's important here, except the next slide. Okay, because there is an experimentalist who claims the problem is solved. Okay. And I'm not going to go into the details of what this experiment was, but it's actually a fairly convincing experiment, which claims that the charge transfer superexchange is the cause of the binding of the electrons. Now, what superexchange is really nothing but exchange, except it goes through, it's exchange between the copper spins, but going through the oxygen. That's superexchange. But it's the basic exchange interaction that most of you should know from quantum mechanics. So it is possible for Coulomb interactions to cause this attraction. So in some sense, if this is correct, then the superconductivity in the high TC cuprates is caused by this superexchange interaction. So it's a magnetic interaction. Now, how many people actually believe this? Not in this audience. If I went to a conference of so-called cuprate experts, how many people would believe this? Well, 50-50. That would be my guess. So the bottom line is still out. However, and there are still people working on this problem. And one of these people may have actually had the answer. Okay. And unfortunately, Steve gave away that I'm 85, so I may soon be one of these people. But anyway, I'll keep working on it, believe me. It'll be around.
Which 50 are you in?
What?
Which 50% are you in?
I'm in the 50, well, I'm in the 50, good question. I'm definitely in the 50% that says it's a magnetic interaction of some kind. It's some kind of Coulomb interaction that is causing this thing. I mean, there are a few people that think it's a phonon, they call it bipolarons, kind of phonon interaction. But it's definitely a magnetic interaction.
Why is definitely?
What?
Why are you putting the emphasis definite? I mean, the theorist's argument probably goes, it will be so boring if it's phonons. It
No,
better be definite.
Well, it really can't be phonons. But there, but there are theorists who would say bipolarons.
No, but why do you say it can't be phonons? Let me just...
D-wave. I don't think you can get a
You can
D-wave.
very easily get D-wave.
Okay, I'm in trouble. I knew it was a mistake to invite him. I knew it was a mistake.
You just need some kind of local phonon.
Okay.
I'm not saying it's phonons, but the way
Good.
it's dismissed is more or less like, how can it be phonons?
I know
the way you were dismissing it.
You love phonons, and I know that. And
You know why?
Yes.
Because 99.9999% of superconductors are phonon.
You're right.
Comes razor.
You're absolutely right. And I'm going to show you something that talks about phonons. And then I'm going to show you why it can't be phonons.
All right, you're on.
Okay, I need to get you on the pickleball court. I can't beat you. I can't beat you in science, but I can. Okay, sorry, I'm losing track of. Oh boy. All right, fine. Don't worry. All right. So look, there are many other interesting, what we call unconventional superconductors that are not driven by the electron-phonon interaction. Okay, and probably all of these materials fall into that category. There was a talk by Pablo here about a month ago, talking about these very interesting twisted bilayer graphene materials that have phase diagrams rather similar to what the cuprates look like. And we don't know the mechanism of these things, but my guess is it's going to be. But we'll see. Shankar may turn out to be right. Okay, so the superconductivity problem is solved, sort of. And what about the normal state? Because the normal state is actually in many ways more anomalous than the superconductivity. Okay? It doesn't look at all like what you would expect for a typical metal. So what do you expect for a typical metal? And I'm going to just talk about transport properties now because that's what I do experiments on. You don't have to know where these formulas come from, but I'm going to talk about resistivity, magnetoresistance. In other words, how does the resistance of a material change in a field? Thermoelectric power, which has to do with how the electrons move under a thermal gradient. And there are certain predictions at low temperature that you should get for a conventional metal, a non-correlated metal. The resistivity should go like T squared, the magnetoresistance should go like the magnetic field squared, and the thermal power should go proportional to the temperature. So what did we actually find when we measure the cuprates? Okay, so I'm going to show you what we find in some of the cuprates. First of all, long time ago, in the normal state, here's the superconductivity, the normal state of this cuprate, linear and T resistivity was found down to about 8 kilo. Now, as Shankar said, if you have electron-phonon interactions, then you expect to get a linear and T resistivity caused by electron-phonon scatter in the normal state. So that is certainly a possible explanation for this in this material. However, we did an experiment here on an electron-doped cuprate. Krislov was intimately involved in that experiment. In the normal state of this particular cuprate, we found that this linear and T behavior persisted down to 35 millikelvin. So that definitely cannot be explained by electron-phonon interaction. You cannot get a linear and T resistivity down to such low temperatures. So this is the signature of a, quote, strange metal state. Okay? And there is no explanation to date for linear and T resistivity in strongly correlated materials. I'm going to skip this one. Okay, so let me just show you a few other properties. This is what the electron-doped cuprate phase diagram looks like. This is doping, okay? This is the temperature. Here's the antiferromagnetism. It's actually a simpler phase diagram than the whole dope ones that I showed you before, but it doesn't really matter. It's dominated by the magnetism. When the magnetism goes away, the superconductivity appears, and actually a lot of things happen at a particular doping here where the Fermi surface actually changes. Okay, and I'm not going to go into the details of that. It's called a Fermi surface reconstruction. That's something that you expect if there is, say, antiferromagnetism or charge density waves in a material. It can change the Fermi surface. It can reconstruct the Fermi surface, and that will change the properties. It's not essential to what I'm going to talk about. What I want to talk about that is new and important is that when you go from this doping, where this Fermi surface reconstruction occurs, into the more metallic region, all the way to the end of the superconductivity, so over a range of doping, you find this linear in T resistivity at low temperature, you find linear in H magnetoresistance, and you find a logarithmic thermal power. So all three of those properties are totally different than the standard Fermi liquid here. Okay? So whatever is happening here in the normal state is very unconventional and unexplained, actually. And why it should occur over a range of doping is also unexplained. There are ideas that something called quantum criticality. If you have a, let's say you go from a metal to an antiferromagnetic state, you can have at T equals 0 something called a quantum phase transition. So you go from the metallic state to the antiferromagnetic state at T equals 0, and that at that point where that happens, quantum critical point, and then you can have fluctuations, quantum fluctuations associated with that point, and that can lead to a T linear resistivity. But that only is at one doping. Here, we're seeing this over a range of doping. So there's something else going on here. It's possible that this is a quantum critical region over a range of doping, but that's not clear why that should be. Okay, anyway, so I'm going to skip this because I basically told you the answer. But, and I'm running out of time. No, I'm not running out of time. It's good. But I'm getting tired of standing here. Grab a seat, yeah. All right, so here's an interesting result that's not understood that we found from our work on electron doping rates, that the coefficient of the linear and T resistivity seems to scale with the TC. In other words, as TC goes down in this, what's called overdoped region, the coefficient of the linear term decreases. And also the coefficient of the magnetoresistive term decreases with doping, and the coefficient of the logarithmic thorough power decreases with doping. So all, as TC goes down, all three of these coefficients go down. So it looks like, in some way, there's some relation between whatever's causing these strange metal behaviors and the TC. But this is unexplained. Okay, so I'm expecting Nassim and Shankar and Jay are all sitting together. They're going to work it out by the end of half an hour, guys. Get with it. Okay, so similar behavior has been seen on the whole dope side. Okay, so all of this strange metal behavior over a range of doping is now currently a very important problem, I think, for understanding correlated, at least the correlated group rates. Okay, so don't bother reading all this. There are many unresolved problems in the hoop race. So even though Seamus Davis, whose experiment that was, who claims to understand the ITC problem and understands the mechanism of superconductivity, maybe it's solved. But there are all these other questions that mostly have to do with the normal state that are not understood. And basically, BCS theory works because the normal metal state is understood. It's explained by something called Fermi liquid theory. It's worked out a long time ago. And using Fermi liquid theory, BCS were able to work out the theory for superconductivity. But we don't have Fermi liquid theory working in these materials. So how does the superconductivity come out of this strange metal state? This is an unknown problem, a very currently active problem. Okay? And that's it. Now, hoop rates are not alone. Very recently, there have been some nickel oxide superconductors discovered. Those of you who know the periodic table, nickel is right next to copper. Okay, so you might expect that, oh, I could fool around with the valence of nickel and get something like the copper oxides. Well, that's in fact what these people here have done. They made a material. Of course, this is not a new idea. People tried to do this 30 years ago, but were unsuccessful because this is experimental physics. Sometimes making the materials you'd like to have is not so easy. And that's part of what I have to do. And JP didn't show up, but that's what he has to do. Okay? He had an excuse. He told me why. I told him that I could now make fun of him. Okay. Anyway, notice that in these so-called nickelates, that the phase diagram, the TC as a function of doping, looks very much like the hoop race. There's this kind of dome of superconductivity. People who want to get papers into Nature now, they make all these beautiful colored slides that I have no idea what the hell it means. Okay, but I do know that at some doping, there is this normal state linear and T resistance, which is not understood in this material nor in the hoop race. And very recently, under high pressure, someone has taken this compound, put it under pressure, and found an 80-degree superconductivity. Now that's pretty high. That's really getting up there near the hoop race. So, and there's also a linear and T resistivity above the superconducting transition temperature. So these are one of the new hot areas where people are trying to look and trying to understand this. Okay, but unfortunately, this word high pressure is not good. Okay? And you can put pressure on materials, we do it in our lab, but it makes all the experiments much more difficult. Nevertheless, this is an interesting recent development. By the way, the aim of this talk of mine is not to explain anything to you, but to just give you a feel for what's going on in this field. Okay? So even though I'm an old guy, I still think this is a really interesting field. Okay, there's a lot of good stuff going on. And in fact, I would call this the dark energy, dark matter question in our field. Strongly correlated. What are the properties of strongly correlated materials? Okay, we don't understand. It's a big mystery. Okay. Maybe Shankar understands it, but mortals like me do not. Okay, now we're going to talk about a different type of superconductor. Okay? High TC from the electron-phonon interaction. Now, about 1968, okay, I just had graduated. Neil Ashcroft predicted that if you could make hydrogen metallic, hydrogen normally comes as H2. It's very hard to make metallic hydrogen, but under high pressure, you might be able to do it. And if you had metallic hydrogen, then you would expect a much higher TC for superconductivity. Why? Primarily because of this term in the front of the BCS expression, the average frequency, lattice of the frequency of the lattice, because hydrogen is such a small mass, the frequency is going to be higher, and therefore TC might be higher. Or the same electron-phonon interaction, of course. Electron-phonon interaction matters, but this matters too. Okay. Now, then of course people ran off and tried to do this, but it requires extremely high pressures. Okay? Millions of times the Earth's pressure, atmospheric pressure. And so not easy experiments to do. So later, Ashcroft predicted or recommended maybe looking at hydride materials. Okay, materials that have hydrogen in them, but not pure hydrogen. Maybe they would have high TC, because again, you might expect high frequency vibrations from the hydrogen. And then theorists got involved. Now, theory today is not the theory of 50 years ago. Theory today is making massive use of computation, using computers. And you can actually make, although I have no clue how this works, you can actually predict crystal structures based on theoretical computational methods. So there's a scheme for predicting crystal structures, and once you have a crystal structure, then using the standard Miguel-Aliastro theory of electron-phonon superconductivity, you can predict what the TC of a material is. So these people here in 2014 predicted that you might get a TC of 80 Kelvin at this high pressure in hydrogen sulfide. Any of you know what hydrogen sulfide is? It's a gas that you don't want to be around. Okay? So you might imagine this is not going to be an easy experiment to do. You have hydrogen sulfide gas, and you have to somehow put it under 160 gigapascals of pressure. Okay? But there are a few experimentalists who are willing to do this. Okay? And they did it. They did it. They came up with a way of condensing hydrogen sulfide into a solid form and put it into a diamond anvil cell where you can get extremely high pressure, basically two diamond tips brought together. You can get very high pressure. And they managed to get electrodes onto the diamond, into the diamond cell so they could measure the resistivity. And lo and behold, what did they find? They found superconductivity of 203 Kelvin. Okay, so this is way, quite a bit above where the cuprates were. And this is driven by the electron-phonon interaction. Okay, so you can get high TC with the electron-phonon interaction, which I think is a big surprise to people. I think one of the main evidences that it was electron-phonon is something called the isotope effect. They substituted for the hydrogen in this sulfur hydride, they put deuterium in, so that's a different mass that's vibrating, and TC went down, as you would expect from the BCS formula. And later on, of course, they did critical field work as well, and they showed that this transition could be moved in a magnetic field, so it was indeed superconductivity. And believe me, these are very difficult experiments to do. So you cannot do a lot of the traditional experiments you would do to verify superconductivity, like magnetic measurements. Eisner effect is usually very important to measure. And these experiments have now been confirmed by other groups, which is very important in any science. All right, so now we have hydrogen hydride. So this is a hydrogen-containing compound that has a very high TC. So of course there are now people working on this. There are maybe 3 or 4 groups in the world, maybe 5, that can put high pressure onto things like this. So the more recent one, 2019, lanthanum hydride, which is basically lanthanum with 10 hydrogens, okay, can be stabilized under high pressure and then measured. And again, superconductivity was found at even higher temperature. Here's the isotope effect. Here's the critical field data. And at least 2 groups have done this. So I think this work is quite believable. Okay. So now we have a new TC versus time picture. Here are our Cook rates, but now we have these compressed hydrogen-containing compounds. So I would say this is a very exciting area now of research. And I'm going to show you not only it's very difficult experimentally, but computationally, lots of predictions have been made of hydride-like materials that could be superconducting. Okay? It's just very difficult to make them. Now, these are binary hydrides. We haven't even gone to the case of ternary hydrides, and there are predictions starting to come in now for ternary hydrides. So this is a very active field, and I don't know whether we will eventually get quote room temperature out of this. Here is somebody, I won't say who, right now, reported they have made a room temperature superconductor. It's got published in Nature, that journal that's maybe right half the time, if that, okay, but it's certainly not been verified or believed. Okay? But these results are believed, and the computational results for predictions are believed. So I think something's going to happen in this field. Well, something's already happened. Okay. But of course, you need this extremely high pressure, which is unfortunate. I mean, that's when you have to have a high pressure to stabilize these materials. What we'd ideally like to do, of course, is to make a material at high pressure, stabilize it, and then relieve the pressure, and we'll end up with a metastable phase. We could then have an atmospheric pressure and measurements. That is certainly possible, and I think will happen. Okay, but of course, there have been some bad actors in this field too, unfortunately. Here was a paper published in Nature claiming this material was a room temperature superconductor at almost ambient pressure. Well, almost ambient pressure, 10 kilobars. That's 1,000 times atmospheric pressure. Okay, so is there that much difference between 1,000 times atmospheric pressure and 1,000,000 times atmospheric pressure? Okay, they had to write a headline like this to get it into Nature. Okay. So that looks very convincing, right? R versus T, going to 0, very nice. Unfortunately, it's all wrong. Okay. So other groups tried to reproduce this, but because there are always people who want to try and make a name for themselves, and sometimes do foolish things. And that's what's happening here. so this paper got retracted. Okay, so, and the person who's the main author of this paper hopefully will get retracted as well from his university, but we'll see. Nevertheless, I am optimistic about this field of high drives and high pressure getting us to higher temperature superconductors. Okay, now this summer there was a report of a room temperature superconductor, LK99. How many of you heard about this? Okay, good. How many of you read or listened to Schonfer's Twitter accounts? Oh, really? Wow.
I killed it.
See?
The Korean stock market went down. But
Yeah, you did. I wish you had told me before you make that comment.
Sell short.
yeah.
Because you partially based it on my skepticism.
Actually, one of my sons called me and asked me, do I really believe it's not? I think this company.
Really? Oh, yeah. Well, I had people call me up. The main person that called me up when this came out. Okay, so this is supposed to be a room temperature, ambient, above room temperature, superconductor. Okay, it's actually a phosphate type material, LK99. I won't go into the details. But, you know, here's the resistance versus temperature. You'll notice the resistance actually doesn't go to zero. Okay, looks like there's a transition. But this is kind of interesting. This is a critical current measurement. So you put current through the material and you measure the voltage. And you see here's a whole range of voltages where you're putting, currents, where you're putting current in and nothing happens. And then you hit a high current and it jumps to the normal state. Well, this looks like a critical current, as you would expect in a superconductor. And they actually showed this material there is levitating. Okay, now levitation is, you think, hey, Meissner thing. Okay, so an initial look at this thing, it looked pretty convincing. People started running around and Schonfer started writing Twitter accounts and people started following him. They actually don't know Schonfer. So why are they following him? Anyway, he wrote some very good comments about it, which is good. And I had somebody call me up who was a hedge fund guy. Okay, what was he worried about? He was worried that all the copper stocks that he owned were going to go down to zero, because if you have a wire that works at room temperature with no resistance, you will put the copper companies out of business. Okay, at any rate, it soon became very clear that these guys had made errors. Okay, so very nice people. This was a polycrystalline material that they had, so it had some impurities in it, of course, and impurities can sometimes really value up in our field. So this group here at the Max Planck Institute made crystals of this purported LK99. And of course, when they made the crystals and measured them, they were insulators. So pretty quickly, this all got debunked. But nevertheless, it was a very exciting time this summer for about a month. And I think it brought a lot of, what's the word? Eyes. A lot of eyes appeared on superconductivity. So actually, when I was playing pickleball, people know that I work on superconductivity. And I said, oh yeah, now I got this is going to be a superconducting ball we're going to use. And man, I know how to control it. You don't. Okay, so now, okay, so what do I believe about superconductivity? I believe there will be a room temperature superconductor at ambient pressure in the next 30 years. I may not be around to see it, but let's see, who will be around to see it? Somebody up here will be around to see it. I think it's going to happen. I think there are enough. I don't think it's going to be one of these strongly correlated copper oxide-like materials. I think it's going to be something else. But just the fact that it has been demonstrated that the electron-phonon interaction can lead to such high TC is, to me, a rather dramatic result. So, yes, phonons are important, just not in the cuprates. Okay, now, okay. Unfortunately, you have to listen to me for 10 more minutes. What time did we start? Doesn't
Five
matter.
after.
Oh, yeah.
Yeah.
We can just go on and on and on. Like all those other colloquium speakers. Okay, no. So I am going to talk about something else. Where are we going to look for these superconductors? Well, there's a whole roadmap of where you might find this in the highlights. I'm not going to go through this. But this is where I want to bring up, I'm sorry about the quality of this slide, but this is where I said theory has become very important in this field. So if you could read, I can't make this bigger, can I? Anyway, these are two very recent papers that are basically using machine learning type of techniques to try to find new hydrogen-containing compounds that might be superconducting above or superconducting anywhere. Okay, so these kind of techniques are now being applied to this field. And both of these papers actually predicted, using different techniques, the same material that might be a ternary highlight that might be a superconductor. So I think people will, of course, be looking for this. So this is one of the reasons I'm optimistic. Okay, enough about high TC superconductivity. There are other things going on in the field of superconductivity, and I wanted to highlight some of the work done here by Nick Butch and Jean-Pierre Paglioni, which has got to do with the discovery of a spin triplet superconductor. Now, spin triplet superconductivity is very rare. Okay, helium-3 as a liquid is a triplet superconductor. Been known for a long time.
Superfluid.
What?
It's a superfluid.
Superfluid, sorry, yeah, superfluid. But unfortunately, we're not going to be able to use that in any way. But there are very few spin triplet superconductors. Spin triplet means, of course, the spins are not this way, and you can compare that they're this way. Okay. And that means that the orbital symmetry, of course, has to be odd. So it's typically p wave, you have p orbital things. And with p orbitals, you can have all sorts of possible superconductor wave functions. I won't get into that, but who cares whether there's a triplet? Well, Chandra gave a talk a couple of weeks ago where if a spin triplet superconductor is topological, it possibly could be used in quantum computation. And of course, possible means there's a long way to go. But the TC of this stuff is around 1.6 Kelvin. And this was discovered about 5 years ago. And this has been generated a lot of excitement. So there's a lot of papers now that have been, a lot of experiments done on this uranium telluride 2 material. Okay, and there's a lot of very interesting properties about it. The thing that might be relevant to topological behavior, topological superconductivity, is something called chiral, which means that time reversal symmetry is broken in the superconductor. That is actually important for using it in quantum computation. So what's the evidence that this thing is a triplet superconductor? Okay. Well, of course, you can't tell from the resistivity. Okay. But what you can tell from is something called the night shift. The night shift is an NMR technique that measures the spin susceptibility of the Cooper pairs. Okay. So when you have a regular S-wave superconductor or even parity superconductor that spins like this, when you enter into the superconducting state, you expect the night shift. Here's the superconductivity. You expect the night shift or the spin susceptibility to go to 0. But you see in this work, the spin susceptibility, which is this data here, doesn't change at all when you go through the transition temperature. So this is very suggestive that you have a spin triplet type of pairing. The other suggestion for that is the critical field itself. So if you measure the magnetic critical field well, they did it in 3 different directions, in a typical S-wave superconductor will have a limit, called the paramagnetic limit, It's the field at which you would flip the spins. At that field, you basically destroy it with repair. However, if it's a triplet, you don't. And so the critical field can get much, much higher. So this is some fairly convincing evidence that it's triplet, but of course more work has to be done. And just to bring this back to Schomburg's talk, then there's the possibility of topology, this being a topological superconductor. Here is the stuff that Schomburg talked about during his talk, where we have proximity effect, superconductivity, where you can get what I call marijuana modes. Okay. That's the only time I can understand it. Oh, sorry. I don't know. Is that legal yet?
Yes.
Okay. I hope so. We're very slow on this drug stuff.
I know a place in Silver Spring.
Oh, you do? Actually, I found one in Bethesda. I'll let you know about that. Okay. Anyway, topological superconductivity is a very interesting field right now. And if you have a P wave orbital part of a wave function in a superconductor, and it has a chiral behavior, it means its phase will change around the Fermi surface, and that can be used for topological computation, although don't ask you how. Okay, but there are enough people interested in it. Okay, so I'm going to probably end pretty soon. So there is evidence for this topological superconductivity. I won't talk about this one. This is an STM experiment, but supposedly chiral surface states have been seen. Time reversal symmetry breaking has happened. This is the Kerr effect. The Kerr effect measures the magnetization. Basically, in the superconducting state, you start seeing a Kerr signal, which suggests triplet time reversal symmetry breaking. Two order parameters. This is some work done here at Maryland. It's been Ian Hayes done this two-component order parameter. Okay, so I'm going to skip all this, and I'm going to just summarize. Okay, I think superconductivity is still a very hot topic. This is a major unsolved problem. I think cuprates, even though they've been around a long time, are still interesting. Hydrogen-rich materials are a very important area of research. I think topological superconductors are a very interesting area. There's still a lot of unknowns about uranium telluride, but anyway, but finally, I am optimistic that something very interesting will happen. Now, will it be practically useful? That's a whole other problem. Okay, because suppose I had a room temperature superconductor. It's probably not going to be like copper, that I'm going to be able to easily make it into wires or easily use it. Even now, after the cuprates, what, 35 years later, they have made wires out of cuprates. And remember, cuprates are like your dishes, your ceramic dishes. You drop them on the floor and they break. It's not easy to make wires out of this stuff, but people have done it. So I think if a room temperature superconductor is discovered, very clever material scientists will figure out how to make wires out of it and how to use it in electronic circuits. But I'm afraid we're not going to have the Dick Tracy levitating parts. That's the one thing we're going to miss. All right, anyway, thank you. Yes? Ted?
Going backwards, I'll ask my last question first and wait for the other. On this spinning triplet superconductor, have people observed the Josephson junction type phenomenon in that kind of a superconductor?
Okay, that's a good question.
Qualitatively different?
Yeah, it would be qualitatively different. And those experiments have not yet been done. People are trying to do them. Absolutely, yeah. So in fact, the way that you measure the phase of the order parameter is a type of Joseph's junction type of experiment. It's a quantum interference experiment, and you need a Josephson junction, or tunnel junction. So those experiments are important and they're being done, but there's no answer to it yet on the triplet. Now there was another material that people thought was a triplet, strontium ruthenate. So for 20 years, people thought from all the experiments done that strontium ruthenate was a triplet superconductor. And people did do those tunneling experiments, and they claimed to see what should happen from a triplet. Okay. But then, about 2 years ago, someone redid that night shift experiment a little more carefully, and they found out that the night shift experiment was wrong. That actually the night shift went to 0 rather than not going to 0. And then all of a sudden people realized, hey, someone did the experiment not quite right. There was something going on. So what about these guys who did this Josephson tunneling? Well, we haven't heard from them. So, you know, some of these experiments are quite difficult.
He still believes it's P-wave, it's triplet, but it seems like it's only one person in Penn State and one person in University in Urbana saying that's one.
Oh wait, I thought that the guy who did this was at Penn State.
Yeah.
Yeah, but he believes it.
Yeah, I just visited him. He was very sad.
Yeah.
He asked me what I believe. I said, I'm not following the science at all. Because everybody believes it's S-wave.
Yeah.
He said,
Well, not S-wave.
Tony Leggett, he claimed not regular S6.
Yeah.
He and Tony Leggett still believe apparently it's.
I see. Anyway, but
Comments about that. I think P-wave can be consistent with spin sigma on general grounds.
okay.
So it is possible that it could be P-wave.
You can get P-wave and spin shift.
It's possible on general grounds. You get some additional orbitals for the fermions.
I see. Okay, well, you know, these guys have gone way above my pay grade. But, you know. But the whole idea of a spin triplet is a very, you know, trying to find spin triplet superconductors is an active area of research. Okay. I don't know why there's so few of them, actually. Yes?
Can you provide some kind of historical context behind the truth rate discovery in the sense that was there like some theory?
Aha, that's a
that was
good,
guiding
okay,
them? How
yes,
did people make this?
good question. Because yes, theory definitely guides the experimenters. You can't just, particularly these are compounds that have 4 elements in them. You can't just randomly put these together and expect something to happen. So the motivating theory was the electron-phonon interaction. There were predictions that in certain oxides, you would have something called a strong Jahn-Teller effect. And that would be kind of would give you a stronger electron-phonon interaction. So the people who found these cuprates were looking at oxide materials that they knew had strong Jahn-Teller interactions. And then they discovered superconductivity, and I'm sure they thought it was driven by this mechanism. Okay, but it was soon shown that it just could not be phonons. Although Shankar still thinks it might be, but I don't see how it could be phonons.
No, I'm not saying phonons are like, but I'm saying nothing definitive has been shown. That's all I'm saying.
Okay.
I'm agnostic.
There are two things that bother me, unfortunately, about the cuprates. First of all, if it is a magnetic interaction, can we come up with a formula similar to the BCS formula? The BCS formula is very helpful for experimentalists. You know, look, TC is related to 2 or 3 parameters, and we might know how to adjust those parameters. But there's no equivalent formula yet for these magnetic interactions, other than, hey, it's somehow related to the exchange interaction. Well, okay, does that mean that if I make a big exchange interaction, I'm really going to get a higher TC, or is there something else going on? So it's still in a state of flux.
Yeah, well, there's, just last week, there's a PRX article that just came out, explains the whole thing.
Really? And what's the answer?
It's not a Twitter X like,
Yeah.
it's PRX.
That's all right.
I'll explain.
Something connected to the less.
And the answer is?
The answer is it's Coulomb repulsion divided by the hopping interval.
Oh.
And a few other ones. All
Okay.
done by first
Okay.
principles.
But look, I think, you know, to me, it's extremely interesting that you can pair electrons via a Coulomb interaction, right? I mean, electrons repel. Coulomb interaction is very repulsive. How the hell do these things pair? Now, these guys understand it. Sure, they cannot be at the same place, okay? And They have to be, the pairing electrons have to be separated, whereas in the electron phonon thing, they're not. They can be at the same point in space, but they're just not there at the same time. So, yeah.
Just a comment about the simple BCS or electric formula is not simple.
No,
But
that's why I didn't show
it can
it.
be computed.
Yeah,
But the point is, so some point in the early 2000s, there were the C60 superconductors.
yeah,
And those, I think, there was some confusion about whether they were electron phonon or
Yeah.
not. And eventually, these guys said electron phonon. But the TC there goes, as you increase the lattice constant, the TC goes up until it goes insulating at some point. But right before it goes insulating, these Eliashberg formulas fail very, very badly.
okay.
I'm guessing again for your hydride materials, Eliashberg theory doesn't work very well because you said the prediction was 80 Kelvin, turned out to be a 200 Kelvin superconductor.
Well, no, but that's what they're using, the Eliashberg theory.
To make a prediction, but
To
I'm
make
saying
their
that the
predictions of TC based on certain crystal structure. First you have to make the crystal structure prediction, which is, to me, challenging. I'm not quite sure how they do that. And then once they think they know the crystal structure of a particular hydride, say, then they apply the Eliashberg theory.
I'm sure the FTS, the crystal structure of Cooper is pretty good.
Cuprates, I don't know.
I'm sure.
I won't. No, I only know that these kind of calculations are being done for hydrides now. Maybe they're being done for others.
So let me make a quick comment on this. So let's say Coulomb interaction is relevant.
Yeah.
I have two comments. One is that many anticoulomb elements. Why does it show up in this very complicated 4-element compound if it's just some kind of exchange? It's Occam's razor. So that's one. Second, if you look at the Coulomb interaction energy scale, then the question is reversed. Why is TC so low? Because Coulomb energy scale here is electron volt, and TC is 90 Kelvin. Okay. So the point is that it's not
Screening.
just screening doesn't change the sign of interaction.
Okay.
So what I'm saying, same Coulomb interaction.
Yeah.
People who believe Coulomb interaction, their logic goes like, it is so complicated to calculate anything that you cannot calculate anything. So it must be Coulomb interaction. Okay, if you say phonons, then you have to be able to calculate. Again, I'm not saying it's phonons, but same Coulomb interaction is just like saying we don't know what's going on.
Well, they do calculations. These are typically numerical.
No, those calculations that you are thinking are exactly like electron phonon interaction. You just substitute paramagnon or plasmon or some other entity there.
Okay,
You
that's-
completely
that's-
ignore the fact that Coulomb interaction is repulsive.
That's a
You know
little
what I'm saying? You just use a bosonic group. Those are phonon calculations, which is a different thing. So this is a problem. The Coulomb interaction scale, as you know, is huge.
Yeah.
Is
Right.
huge, and TC should be like 1,000 Kelvin. So again, I do not go around saying all my friends will hate me that I don't think it's Coulomb interaction. I'm agnostic. I do not think it's a very explanation.
Nobody's going to hate you, Shankar, except for some of those Twitter comments. that you-
No, but this is my philosophy.
Yeah.
It's agnostic.
Okay, let me, Jim.
So, I have a question about the way you guys do your experiments and what you're actually measuring.
Okay.
In all these things that you show, you're basically looking at some transport problem.
Well, I do that.
Right.
Other people do
Okay.
other things.
I'm just wondering, is it impossible to measure the phonon spectrum in these experiments?
Oh, no, you can measure the phonon
And
spectrum.
don't you learn something from this? I mean,
Yeah,
you
yeah.
didn't mention anything about it.
Absolutely. Well, I didn't mention that, but yes, and in fact, measuring the phonon spectrum can certainly be done by neutron scattering and with large crystals. And in the more traditional superconductors, there's a parameter called alpha squared F omega, which is related to the phonon spectrum, frequency dependent of the phonon spectrum. And that is the measurement of that phonon spectrum and seeing it in a tunneling experiment is what convinced people that the electron-phonon interaction was, in fact, what was going on in traditional superconductors. But that experiment done here...
This argument back and forth, you're making a phonon and non-phonon.
No, but this experiment doesn't show... That same experiment has been done in the cuprates and does not show a strong coupling to phonons, as far as I know.
ZX Shen would claim no. There are features. It's a very complicated...
But not in tunneling.
But there are 21 different phonon nodes in YBC. Okay? It's not exactly aluminum. So
Yeah,
it's
no,
a very
exactly.
complicated question.
Okay. Well, see, now you know why this is still an exciting field, right? I mean, we can't even agree. Of course, I have no idea what he's talking about, but that's yeah,
Well, I also have an experimental question
yeah,
about the strange metals
yes.
and about transport. So
Okay.
transport quantities are measured, if I understand, essentially by two-point functions, two correlations between 2 points and maybe Fourier transforms of them or something like that.
Well, we don't do anything that way.
Anyways, it's 2 points.
No, it's four, yeah, well,
The
it's,
rate to go from here to there of some kind of quantity. What I'm wondering is the following thing.
yeah,
I knew that
it's
from...
much simpler than that, though.
Pardon?
It's much simpler than that.
Okay,
We pass current through the material and we measure the voltage.
right. So what I want to ask is,
Yeah.
this. I'm familiar from free field theory that 2-point correlation functions, which I think is basically all you're measuring, determine all correlation functions, whereas in complicated interacting theories, higher point correlation functions carry important new information. So I don't understand why you guys never report experiments where you measure higher point correlation functions if you're interested in something like a strange
Well,
metal and understanding what
okay,
it is.
we would do it if we could think of a way to do it.
And it's done. Noise spectrometry, that's exactly what it's doing. Noise, because
Yeah.
in transport, the noise associated with transport is connected with those things. But the experiments become much, much more difficult. That's the main point.
But actually, a noise experiment has been done.
Yeah.
And the noise experiment also does not look like traditional Fermi behavior as expected. Okay, so I didn't know that noise measures this other correlation. But we do things much simpler than that. I mean, these transport measurements are, pretty simple, really.
Right, but I'm asking, why don't we do things more complicated?
It's very simple, I'm lazy.
Okay, can I follow up with a theory question?
Uh-oh.
It's really
Sure.
an opinion about theory. So
Yeah.
in the field of quantum gravity, we intersect with you guys through severe Sachdek.
Oh, yes. Oh, Sabir has a theory for
You
everything.
said that nobody understands strange metals, but he apparently understands it, and they're holographically dual to black holes. I want to know what
They are.
I want to know, why didn't you mention that?
Well, very simply, because who cares? No, but I mean, no, I agree with you. Subir will come and give a seminar here, and everything will be explained. Okay? So I'm not saying that idea is necessarily wrong. There's another guy, Jan Zanen, who pushes this idea all the time. But then my question would be, yes, maybe they can explain the linear and T-resistivity by this business, but I'm not even sure they can do that. But they can't explain some of these other things that I showed you, just these magnetoresistance, thermal power, and there's a lot of other measurements. So far, they have not explained it. Okay. Now, of course, if I told Sabir that he hadn't explained it, he would, of course, immediately have it explained. And, yeah. But I think you should invite Sabir and see,
Give it talk on this.
and give a talk, and maybe he'll say what's he thinks is really understood and not understood from the theory point of view. Yeah. So I can't answer that in
Well,
detail.
no, your
But yes.
mode of answering it gave me the answer.
Okay.
Yeah, yes.
No, but those ideas are being applied by some people in this field. Yes, they are.
Quick comment on that. You'd already said that the Sabir's theory and that it was one missing value that they would explain, which would be something, because it's quantum critical.
Oh, his is a
Which has
quantum
not been
critical
seen,
theory.
which has not been seen by anybody.
But you
Okay.
see over
It's assumed.
Okay, yeah.
No, the honest question is that it's a beautiful theory, but it's not clear at all it applies to reality. That mapping is almost impossible.
Well, I mean, I tried to say that one of the surprising things that hasn't yet been explained is why these strange mental behaviors occur over a range of doping and not just at one so-called critical point. That's not understood at this stage. Yeah, you can.
I take one last question.
One last
One
question.
last question.
Yeah, this one has been found.
I told them, it's amazing. Some of my 272 students are still here. Are you people crazy?
You give them an A+.
I think they are moved by the sociology of physics.
They're going to give me a final exam on this book. That's what I'm worried. Yeah.
Well, so I was going to ask
ask you to maybe speculate or give some thoughts on the following topic, because there's a lot of buzz about using machine learning and AI to predict materials, and then having automated self-driving labs to create materials and
Yeah.
We don't need you anymore.
I think.
I'm curious what your thoughts are on that.
My thoughts are, I think that we might get some guidance on materials from machine learning ideas, but so far I haven't seen where that's going to change what we try to make.
What about automated labs where you have high throughput materials?
Oh,
synthesis?
you know, I don't know. That maybe something like that will happen. I know that, for example, Chiro Takuchi, one of the professors here, and JP have written some papers on trying to predict superconductivity from machine learning. So they took a whole bunch of parameters in the literature, mostly I guess on cuprates. And at the end of their paper, they did predict maybe 10 or 20, I think they were oxides, that might be superconducting. Okay, so now the experimentalist has to say, oh my God, now I got to try and synthesize these 20 materials, and you know, they didn't predict the TC, so which ones are going to be interesting TC? Yeah, and LK99 was one of them. No.
All right, on that note, why don't we thank